Imagine a crucial part of an airplane, maybe a bridge, or even your car. On the surface, it looks completely fine, maybe just a tiny scratch. But what if it suffered an unseen bump, a hidden impact? How can engineers really know if that component is still safe? Is it secretly compromised? Welcome to the Deep Dive. Today we're diving into some really cutting-edge research that tackles exactly this challenge. We're going to unpack a fascinating paper from Oster Overhoff and a team over at Perm National Research Polytechnic University. It's just out in Fracture and Structural Integrity this year, 2025. Our mission for you today is to get a real grip on how these, invisible impacts affect the strength of critical materials. And also, how scientists are developing these brilliant new ways to predict their hidden vulnerabilities long before you see any actual damage. Think of it as a shortcut to being well-informed about these hidden risks.
Yeah, and what's so compelling here, I think, is that we're talking about polymer composites. These are the lightweight, super strong materials used just everywhere: civil aviation, shipbuilding, the automotive industry. They're fantastic materials, but like this paper points out, they do have a specific vulnerability, an Achilles heel, really: low velocity impacts. And these aren't necessarily, big dramatic crashes. We're talking everyday bumps, maybe a dropped tool during maintenance or just accumulated stress over time. But they can cause serious internal damage, things like microscopic matrix cracking or layers separating, which is called delamination, even tiny fiber breaks. And the key is you often can't see any of this from the outside.
Okay, let's unpack that a bit. We really do depend on these materials for our safety day in, day out. So if this low-velocity impact damage is often invisible, why is it such a huge concern? It kind of feels counterintuitive, right? Something you can't see being so dangerous.
That really hits the nail on the head. It raises that critical question. If the damage is hidden, how on earth do you know if the structural integrity is shot? And the research shows pretty clearly that even impacts that seem minor can lead to a significant buildup of internal damage. This fundamentally changes the material's mechanical behavior, how it responds to stress. Especially for laminated composites, their structure means they're inherently weaker when deformed across the layers perpendicular to them. So they're really susceptible to these impacts that push inwards, causing those internal separations, that delamination. The key takeaway, really, is that what looks perfectly fine, totally intact to the eye, could actually have significantly reduced residual strength. It just can't carry the load it was designed for anymore.
Right. So the paper isn't just saying, hey, there's a problem. It's trying to develop a better way to actually assess this hidden influence. And crucially, it aims to pinpoint these threshold values of impact energy. I'm picturing clear warning lines for engineers. How vital is it to actually quantify those points?
Yeah.
Where damage starts to get serious or where the material basically hits its minimum safe strength.
Oh, that quantification is absolutely everything. You need those numbers. And to really understand these hidden dangers, the researchers had to be incredibly meticulous, very hands-on in their experiments. Should we talk about how they set it up? How they did their sort of scientific detective work?
Yeah, absolutely.
Yeah.
How did they actually put these materials to the test to see what's happening beneath the surface?
Okay, so the team focused on a pretty common high-performance material, a structural glass fiber polymer composite, GFRP for short. They carefully prepared specimens, basically small, flat panels, and this is important. They used two different fiber arrangements. They call them reinforcement schemes. One had fibers lined up with a perpendicular to the panel edges. That's the 090 scheme. The other had fibers laid at a 45-degree angle, which is known as 45N. This lets them see how that fiber orientation affects things. Then they followed this really rigorous four-step process. First step, baseline strength. They compressed undamaged samples to find out their original maximum load capacity. That's their starting point, their reference. Second, controlled impacts. They took other identical specimens and subjected them to very precise low-velocity impacts. They used a specialized electrodynamic system for this. They tested 10 different impact energy levels, ranging from 10 joules up to 100 joules. And it was always a single controlled strike with a standardized rounded tip. Imagine dropping a very specific weight from an exact height again and again, super precisely. Third step was damage assessment. Now, after the impact, just looking wasn't enough, obviously. So they used an ultrasonic flaw detector, essentially using sound waves to peer inside, and also optical microscopy. This let them map out and actually calculate the area of internal damage, particularly that delamination we mentioned. And this ultrasonic method, scanning from one side, was crucial because sometimes, with really high impacts, the impactor might go right through, making two-sided scanning impossible. So this technique still worked. And then finally, step 4, residual strength measurement. They took those impacted specimens and compressed them again, just like in step one, to see exactly how much load they could still bear after being hit.
Wow, that level of detail in the methodology, it really builds confidence in the results, doesn't it? It means they weren't just, guessing. They were systematically linking a specific amount of impact energy to a measured amount of hidden damage, and then directly to how much the material's performance actually degraded. That feels like the bedrock for any reliable prediction, really. Okay, so once they had this whole setup running, what did the impact tests themselves actually show? How did the composites respond during the hit itself? Was it just a simple crack or break, or was it more complex?
Oh, it was definitely a more nuanced process. The results clearly showed distinct stages in how the material responded, and it depended heavily on the impact energy. At the low energy levels, say around 10 to 20 joules, they saw the material deform under load, reach a peak, and then smoothly unload, kind of springing back. Internally, this matched up with the very first signs of damage, often invisible matrix cracks starting, and the beginning of delamination between layers. Then you move up to medium energy, maybe 30 to 50 joules, and things get more dramatic. You see a sharp drop in the load right after it hits its peak. That tells you the material is rapidly absorbing a lot of energy. And this corresponded to much larger areas of delamination and even actual fiber breakage right on the surface where the impactor made contact. And then at the high energy levels, 60 up to 100 joules, the impactor actually punched right through the specimen, what they call a breakthrough. But what's interesting is even after the breakthrough, the load didn't just drop to zero. It often increased again slightly as the impactor continued to push through and was slowed down by the surrounding, already damaged material.
Huh. So it's not just a simple scale up. The type of damage fundamentally changes as the impact gets harder. What about those different fiber arrangements you mentioned earlier, the 090N versus the IFAV45N? Did they respond differently during the impact itself?
Yes, absolutely they did. While the general patterns those stages were similar for both, the 45N specimens, the ones with the angled fibers, consistently showed higher peak loads during the impact, somewhere between 8 to 22% higher depending on the specific energy level. And the reason for that is fairly intuitive. The angled fibers essentially provide a greater total length of fiber directly resisting the impactor's push compared to the straight 090N layout. It's just more material in the way, effectively. They also pinpointed the breakthrough energy, the point where penetration happens for this specific GFRP material, to be generally around 50 joules.
Okay, now this is where it gets really critical for anyone thinking about safety, right?
Yeah.
How does all this damage, the stuff you see and the stuff you don't actually translate into the material's ability to still do its job? How much strength is really lost after the hit?
Exactly. This is where the core findings really come into play. The team plotted what they call impact sensitivity diagrams. Basically, these graphs show the residual strength. They use the term FCAI, compression after impact strength plotted against the energy of the impact, IMP. And these diagrams very clearly revealed three distinct characteristic stages. First, there's stage one, insensitivity to impact. Up to a certain point, around 15 to 20 joules of impact energy in their tests, the impact had surprisingly little effect on the material's remaining strength. In fact, for many of the 090 specimens hit with just 10 joules, when they compressed them afterwards, the failure actually happened outside the small damaged zone. The damaged bit was still strong enough. This confirms there's a crucial lower threshold, meaning minor bumps aren't necessarily a structural death sentence. But then came stage two, rapid reduction in strength. As the impact energy increased beyond that initial threshold, the material's load-bearing capacity started dropping significantly, quite rapidly. This is clearly the danger zone. And finally, stage three, minimum bearing capacity. After a certain higher energy level was reached, the material essentially hit its lowest residual strength. Further increases in impact energy beyond this point caused hardly any additional strength reduction. The graph basically flattened out into a horizontal line. It had reached its practical limit, its minimum operational strength.
Got it. So clear danger zones emerge from the data, and there's a definite point where the material just sort of bottoms out in terms of strength. Did the fiber arrangement, the 090N versus CR-45N, influence how much strength was lost in these stages, or how quickly it dropped off?
Absolutely. The material showed what scientists call anisotropy in its sensitivity, meaning its response depends on direction, in this case the fiber direction. For the 090 material, with fibers aligned along the main stress direction, its strength was reduced by about 45% once it hit that minimum capacity stage. But for the 45N scheme, with the angled fibers, the strength reduction was significantly less, only about 25%. And this difference comes down to how they deform under load after being damaged. The 090 relies heavily on those aligned fibers bearing the direct compression load, so damage there is critical. But with the 45NN, the angled fibers allow for more complex mechanisms like in-plane shear and some fiber rotation, which provides a bit more resilience against a catastrophic drop in overall strength. And another really critical finding, something that's potentially huge for practical applications, they found a very strong negative linear correlation between the measured residual strength and the measured area of delamination inside the material. We're talking a correlation coefficient below -0.9, zero point 0.9, which is statistically very strong. Yeah, it means as the hidden damaged area, delamination, gets bigger, the remaining strength reliably goes down in a predictable linear way.
So you could almost estimate the strength loss just by measuring that internal damage.
Exactly. That's the implication. It suggests you could potentially evaluate the remaining strength, the FCAI, simply by using non-destructive ultrasonic testing to measure that internal damaged area. That's a massive leap for non-destructive evaluation, potentially allowing checks without having to do destructive compression tests. You can effectively peer inside the material and quantify the hidden danger.
Okay, this brings us to the really practical side. We've got these observations, these measurements, this understanding of the damage stages. How do we package all that up? Turn it into something engineers can actually use day to day to predict performance, design safer structures, make better maintenance decisions. It's about shifting from just reacting to damage to proactively predicting it, right?
Precisely. And that's where the mathematical modeling becomes absolutely essential. The researchers recognized they needed continuous mathematical functions that could accurately describe these S-shaped impact sensitivity diagrams we've been discussing. And, most importantly, these functions needed to precisely determine those critical threshold values where insensitivity ends and where minimum strength begins. They laid out 4 key requirements for any useful function. 1, it has to be non-growing, meaning impact can't logically increase strength. 2, at zero impact energy, it must equal the strength of the original intact material. 3, it has to be limited from below by that minimum bearing capacity we observed. And 4, it needed to capture that characteristic slow, fast, slow shape of damage accumulation, which mathematically means having one inflection point.
Okay, that sounds like quite a complex mathematical puzzle, trying to find a function that ticks all those boxes.
Yeah.
What models did they actually look at?
While they examined 3 specific models, 2 were existing ones based on power and exponential functions. They called them the C and K models. And then they developed a novel one based on the arctangent function, which they named the AT model. The big advantage of their new AT model, mathematically speaking, is that it has a continuous derivative. This allows it to very smoothly reflect those changing rates of damage accumulation across the different stages and the results. All 3 models actually showed remarkably high accuracy in fitting the experimental data points. The coefficients of determination were really high, over 0.96 for the 09 and ZO and over 0.87 for the DAM and 45N schemes. So they all did a good job describing the data. However, the older C model did have a theoretical issue. For the NAR and 45N case, it actually predicted a 0 critical residual strength, which, as we discussed, doesn't really align with the physical reality that a damaged material will always retain some minimum level of strength. So using these validated models, particularly the K and their new AT model, they could then precisely calculate those 2 critical threshold values for the 090 CO scheme. That first threshold, S1, marking the end of the impact and sensitivity area, landed consistently around 18 to 19 joules across the models. And the second threshold, S2, where the minimum bearing capacity is reached, was about 50 joules, which lines up perfectly with that breakthrough energy we saw experimentally. Ah, interesting connection.
Yeah. Now for the 45 scheme, the first threshold varied a bit more between models, somewhere between 10 and 19 joules. But the second threshold, S2, where minimum strength was hit, was significantly higher, up around 92 to 98 joules, much higher than the breakthrough energy for this scheme.
So breakthrough doesn't always mean minimum strength.
Exactly, not for the 7x45N scheme. It highlights again that because the damage mechanisms are different with those angled fibers, penetrating the material doesn't immediately equate to reaching its absolute lowest strength level. There's still some residual capacity being utilized differently. So essentially, this approach gives engineers a really robust, mathematically grounded way to understand exactly how impacts degrade these critical materials, and maybe more importantly, to pinpoint those critical points of no return, those thresholds. That seems like an incredibly powerful tool for design and safety assessment. Wow, what an exploration into the hidden world of material science. We've really seen how even these low-velocity impacts, the kinds that might leave no visible trace at all, can drastically reduce the strength of these critical polymer composites. We learned about the multi-stage nature of the damage, that fascinating anisotropy, how different fiber setups respond differently, and that crucial link between internal delamination area and the actual remaining strength. That connection really seems like a potential game changer for testing, right?
It really does. And maybe most importantly, we explored how these innovative mathematical models, like that new arctangent-based AT model, can accurately predict these complex behaviors. And they let us pinpoint those crucial impact sensitivity thresholds with real precision. Ultimately, this kind of research gives engineers powerful, data-driven tools to design safer, more durable structures, because they can better predict how materials will behave long after any visible damage might be gone, or even if there's no visible damage at all.
Yeah, which leads to a really important question for you, our listener, to think about. Given just how widespread these composite materials are now, I mean, they're in everything from airplane wings and fuselages to car chassis, wind turbine blades, how might this improved ability to predict hidden damage actually change how we approach safety inspections and maintenance schedules? Think about the implications of knowing with real scientific certainty when a component that looks perfectly fine on the outside has actually reached its structural limit internally. What other systems, what other industries could really benefit from this kind of precise, predictive modeling for unseen wear and tear? Thank you so much for joining us on this deep dive. We hope you feel a little more well-informed and maybe just a bit more curious about the amazing and sometimes vulnerable materials that literally hold our modern world together.